Okay, so welcome to the last slot in this conference. My name is Klopp. I'm working for EclipseCon in Stuttgart, Germany. And I have to warn you because what I'm going to talk about now, so the embedded project has not yet anything to do with Eclipse. Nevertheless, it's in the cool stuff track, and I hope it will be cool stuff. Okay, so what I'm talking about is a project which Eclipse has been doing for the last 2 years roughly. It's a project which we do in collaboration with Fortis, German research company, and BMW mainly. And it's about writing embedded software, but with emphasis on software engineering practices. In order to understand why we actually started that project, we need to have a look at the current situation of embedded software development. So, first of all, added value in embedded systems is mostly driven by software these days. There has been a recent study by the Center of Automotive Research in the US, which stated that roughly 40% of a car's total value is actually made up by software. There's another quote from a friend of mine who's working for BMW, which recently told me that they're currently actively looking for software engineers just for the pure fact that meanwhile they think everybody can build cars. So what distinguishes them from others is actually the fact that they have maybe better software, more innovative software, stuff like that running in their cars. So at the same time, many of their embedded systems are running in safety critical environments, which is why high quality or high software quality in general is very important, maybe even more important than it has been so far. And this drives the need for things like test support, follow methods, requirements tracing, all these things, which is typically not there in classical C. At the same time, the time to market becomes shorter and shorter, and this drives the need for reuse and productize. And this is especially important as you need to keep up the innovation speed in these software projects. As the lifetime of software increases, the problem is that the software needs to be maintained for a longer time, right? And this is again something where you get new team members, where they need to read actually your code, where you need to understand the code which you haven't seen before, and all of that we see is pretty tough. C typically does not provide the necessary abstractions for large-scale software engineering. So it's a pretty aged language. There's hardly any support for the modern software engineering principles. Tool support could be better. For example, if you compile in a classical C IDE, or you always need to compile in a classical C IDE to get presented with the errors. Other things, like for example the preprocessor, are more often part of the problem than part of the solution. Stuff like that. On the other hand, there's not really an alternative to C, because the runtime efficiency in these projects remains critically important. So I'm currently involved in a project where we are building a smart meter, and we're actually using that embedded technology, which I'm going to show you. And initially there were thoughts of building that stuff on top of C++, which seems to be the natural evolution to C, right? But the problem is that, first of all, the code becomes slower, and it becomes bigger. And both are things, if you need to produce many hundreds or maybe even millions of pieces, that's something which you don't want to afford when it comes to production, because the better hardware is also more expensive, obviously. So what do we actually do? Well, the idea is if we manage to raise the level of abstraction to an appropriate level, then we can build better tools, we can build better test support, the language becomes better readable, stuff like that. So, again, if we know what the level of abstraction is we should actually work on, then many of the challenges which I mentioned before just go away. But the problem is that this level of abstraction means different things to different people, right? So if we think about software which is written generally in C, that's a general purpose programming language, so I can do everything there. But there is a significant difference whether that software later on runs, for example, in a stock trading system or in a car. So you need different abstractions because these people have different, well, things they're talking about, right? Different things are relevant to them. So what we in the end need are modular extensions which you can build on your own and thus enhance the language you're working with for the task at hand. And this is exactly what we are trying to do with Embedder. So Embedder is essentially an extensible version of C with special support for formal methods, requirement engineering, and product line engineering. So the three kind of key challenges there. But obviously a language is not enough, so we also need an IDE for that. And as an IDE here, we've chosen JetBrains IPS. And the reason why we've chosen that is that it's not a pure text editor. It's a so-called projectional editor, which means that you can mix different notations, you can embed and compose languages, all things which are very, very hard, if not impossible, with classical text-based IDEs. And one example for mixing notations is here, right? So we have embedded a decision table right in our C code. And I'm going to show you later other stuff, which is similar. So an IDE obviously is not enough either. If you're writing software and you're using new kinds of abstractions there, or new notations, whatever, you also want to debug on that level of abstraction. And this is why we also have an extensible debugger, and actually this is where we're using Eclipse. So we extracted the CDT debugger and we are reusing the CDT debugger there. Okay, so let's have a look at Embedder, what it looks like, how it feels, and what the extensions are we are building, what we've built so far. Okay, so I mentioned it's more or less a classical C IDE. So you can program just normal C in here. You get refactoring support. So for example, if you rename that function here, it automatically changes down there in all of its usages. You don't have to do anything for that, right? There are other things, like for example, if you get rid of the pointer here, automatically IDE detects that and changes accordingly. So these are pretty simple things. Now, it's not pure C. So we made a few modifications. One example is that we don't have C files and H files. We only have so-called modules. And if you export something, then the prototype of the thing you're going to export actually shows up in the header, and otherwise it remains in the C file. Just small things which are kind of nonsense in classical C. Okay. So far, so easy. The more interesting pieces begin when we actually talk about language extensions. And all of the things I'm going to show you now are modular extensions, which means you can pick and choose whatever you want, depending on the context you're in, and you can also build similar things for your project, or for your company, or the domain you're in, whatever you want. So the first thing is data structures. So we do not only have classical C data types like int8 or floating point things, but you can also annotate arbitrary C data types with physical units. And so we could, for example, write a function which is int16, and we want to return it meters per second from a physical type. It should be a function which is called getSpeed, right? And we pass it to arguments like an int16 meters, which is distance, and int16, which is time or seconds, so t. And now we could return, for example, t divided by distance, and the type system under the hood detects that this is wrong. Okay, so we can have a look at the calculated type under the hood, and you see it detected that the physical unit, so the physical meaning of it, is seconds divided by meters. Whereas meters per second was somewhere defined as meters divided by second, right? Stuff like that. Also, if you go ahead and try, for example, to add t and distance, it will also complain because it knows that these are two physical units which are not compatible, so you're not allowed to add those things. And this is a very simple extension to C, which has no runtime overhead whatsoever, but probably it would have caused a regain not to explode, stuff like that. Right? So the next thing, if you do large-scale software engineering, you'll most probably need to define something like interfaces and components, right? So if you're from the automotive industry, there's a standard which is called AUTOSAR, pretty popular these days, and this is kind of what we took as a basis to start with, at least from a concept perspective. So you have interfaces in Embedder, you can use interfaces in Embedder. Interfaces have operations, and if you'd like to, you can add pre- and post conditions and also protocol state machines to these operations, which are essentially kind of guarantees and requirements if you're calling this function. Right? So the preconditions would be the requirements towards the caller, and the post conditions would be the guarantees. What you can do now with those things is that, first of all, during runtime, you can obviously generate some asserts, stuff like that, but in an embedded system, that's typically not what you want to do, because that's additional overhead. You want to check that statically before you actually deploy your code. And this is why we integrated various formal verification tools. So in this case, for example, we can use CMDC, so it's a data flow analysis tool, under the hood, to statically verify that we never run into a situation where one of these pre or post conditions is actually violated. Okay? And in case we are running into such a situation, you'll get a counterexample which tells you how you could get into such a situation. So running this tool takes roughly a minute, which is why I'm skipping that now. But you can see here, for example, a component, which is the implementation of such an interface, can be marked as verifiable. And then you can specify, for example, where you want to start your analysis, and additional tweaks for how deep should such an analysis go, right? So, stuff like that. So speaking about the implementation, we have components which actually provide the implementation for these interfaces. But that's typically not enough. You also want to specify what are the requirements in order to provide that implementation, right? So here we have a component which provides track.1, but in order to do so, it needs a track.1 processor. So that's explicitly stated here. Okay? So these provided ports can be optional. Maybe you can serve that functionality without that. So in classical C, what you need to do actually is you need to detect that stuff, and you need to surround it with an if not now. Right? Again, the problem analyzing things like that is very, very hard, because you could have in the very same if an arbitrary amount of additional conditions, which is impossible to detect, essentially. Again, by raising the level of abstractions, requires optional. We know now that things like that actually need to be surrounded with a special statement. For example, let's do that. So now everything is surrounded with a so-called when connected statement. So you have static analysis which detects errors like that right when you're writing code. And if you're generating afterwards and you know that these things are wired, you can optimize this if statement out again. So again, it's not only making your code more safe, but it also gives you more potential to optimize your code. Okay? By raising the level of abstraction. So let's undo that stuff here and go down to an example where I want to show you the integration of formal verification stuff. So here we have a decision table. That's the example you've seen before in your code, in the screenshot, sorry. What does the decision table actually do? Well, it checks if, in this case, the altitude is less or equal than 2,000 meters and the speed is less than 150 meters per second, then the result will be 0. Otherwise, it will be 10, stuff like that, right? So it would be two nested if statements. If you're writing two nested if statements in classical C code, it's pretty easy to just forget something and by that have kind of a hole in your decision table, or like have overspecified the things, and then your decision table will be inconsistent. So here we can now again run a model checker. In this case, it's Yaxis, where you're getting a counterexample or a proof that this decision table is complete, so there are no holes, but it's inconsistent. And why is it inconsistent? Because if you pass these arguments in here, then we can have a look. What happens? Well, the turn point altitude is supposed to be 2000, and here we have less or equals, and here we have bigger or equals. So we don't know actually what the result is. Okay. So by integrating these formal methods, you don't have to, well, it's similar to writing test cases, but with a mathematical proof in the back. Okay? So we can just correct that, rerun the verification, and we immediately get feedback, which tells us, well, now everything seems to be fine with that decision. Okay, another thing which plays a pretty important role in embedded systems is, just let me switch that off, is state machines. So here we have directly integrated state machines into your C code. So from within your C code, you can, for example, instantiate a state machine, you can check whether it's in a certain state, you can trigger these things, typically things which you would need to do with external tools. And then you have some kind of code generator in between. And writing the state machine here is pretty easy. What does a state machine have? Well, obviously in events, out events, has certain variables which it's dealing with, and obviously states and positions between those. You can also visualize these things. You can click here, for example, to navigate. So everything really integrated. But again, the benefit of writing such a state machine is that you can analyze these things. Like, what can go wrong with a state machine? There can be transitions which are non-deterministic, there could be states which are not reachable, all of these things. So classical things which you can derive from that. And these are things which you can typically do with external tools as well. And other things like, for example, Simulink will provide you similar solutions there. And here you get, for example, here you get a counterexample where you can navigate through these things. Actually, double clicking seems not working currently anyway. So you get really kind of a stack trace where you can find out what's the problem. But the more important thing there is that things like non-deterministic behavior, well, that's easy to detect and probably also easy to find. And it does not say anything about the domain context you're in, and it doesn't validate any of the domains. Right? But what you can do with that as well is write custom verification conditions, where you can, for example, we have integrated some kind of header language here, where you can add constraints to that state machine, which then are mathematically proven or not. And all of these constraints which you add there are essentially domain constraints. Right? Like, for example, after 10 times being in the red state, I expect to be in the green state. Stuff like that. Okay, so these are state machines. Another pretty popular thing in embedded software development is variability. So in classical C development, you have a preprocessor and you have typically all kinds of if-thens laying around and definitions laying around. And this is very error-prone and leads to a lot of different problems. So this is why we actually got rid of the preprocessor entirely and replaced it with higher-level constructs, like, for example, you have a feature model here. And inside that feature model, you describe what's the relationship between the features in your software. Here we specify, for example, that if we are using the normalized speed feature, we expect the max custom or max 100 feature to be there as well. And at a later point in time, you're creating these configurations, and you get immediate feedback if your configuration is, for example, invalid. Okay? So from within your code, how do you use these things now? You can go to an arbitrary expression, like for example here, and add a so-called presence condition, which says, well, this one should only be there if the normalized speed feature was chosen. And if you now, currently we're seeing that that whole program in the so-called product line. you can now switch over, of course, it's a projective editor, and say, I only want to see it in the variant, whatever, do nothing. And you see how the program actually changes, and it remains editable. So you can make all these changes here, like for example, go back 3000, see it in the product line view again. Still works. Okay? So another example where it makes sense to use other notations is if it comes to math. So integrating math into an engineering tool makes sense, because many of the tasks we're dealing with are actually mathematical tasks there. So if we would have, for example, vectors integrated or matrices directly integrated into the tool, that would make the thing just much more readable. And also you can integrate custom operators, like here, for example, a cross product or things to transpose a matrix. So another thing is if it goes to dealing with hardware. So in the smart meter project where we're currently working on, we're not using any operating system. It's really programming bare metal. The problem is we want to test that stuff on a PC, but many of the registers which we are using are actually special purpose registers which do some calculations which are implemented in hardware. So when it comes to testing, we need to actually show, or well, simulate or emulate these registers, and that's what we are doing here. So we declare actually that we have a register word, which is called R2, and if I'm writing to that register, under the hood, the value is multiplied by 1 byte, stuff like that. From a user perspective, it doesn't matter. You're just accessing that register and you're assigning it the value 5. And once you read from it, under the hood, it automatically got multiplied by 1000. And if you generate the very same software then for the actual hardware, all these multiplications go away again, and so your software doesn't change. It's not really something you as a software engineer need to deal with. And all such things can be built project-specific, hardware-specific, domain-specific, whatever. Right? You can really mix and compose these languages. Okay, so unfortunately, writing software is not only about writing software. We have, for example, to deal with requirements as well. So this is why Embedded has a language for writing requirements, obviously. But writing requirements is only one part of the problem. Typically, you also want to trace to those requirements and then check whether all these requirements are actually implemented or not. So again, we are making use of the projectional nature of that editor by going back to the state machine. So currently you don't see any traces to the requirement, but you can just switch a flag and then all of these traces immediately show up. And the nice thing is that even if you would copy, cut, paste, move around these things, although you don't see the traces, they belong to that node and they're moved along to that node. Right? So it's kind of refactoring aware. And it's also pretty nice because you can always go to an arbitrary element in your program and say, who is using that stuff? In which context? So here, for example, we want to find out who is tracing to that requirement. And you get immediate feedback and see, well, it's traced here and it's traced here. So having some kind of impact analysis is built in. Okay, so the last part where we need to deal with in software development to deal with is documentation. And this is also something which is, typically hard to deal with because documentation is kind of always outdated. Many of the reasons for that is that you can't directly link to the nodes or to the program elements. And this is something we dealt with here as well. So for example, we are referencing here directly a track point, right? And if you're making modifications to that track point, or in this case just renaming, the IDE knows about that and renames all of the documentation stuff as well. Another thing is that you can embed all kinds of visualizations. Or this here, for example, when you generate out of that document HTML code or LaTeX code, the text behind that stuff is actually automatically copied in that place. So even if you add, for example, here a new argument and you regenerate that argument automatically shows up. Another thing is visualizations. For example, you always get these live updates of these visualizations all over again. And again, the documentation language is something which you can extend by your own concepts. Like if you're having a special language which you want to build in here, or you have special, I don't know, things how you want to deal with the documentation, validate the documentation. These are constraints which you can add. And obviously, as it's a projectional editor, you can show images inline. So it's kind of a word for writing documentation for programs. That's the ultimate goal. Okay, so going back to the slides, the embedded stack. How does it look like? Well, at the very bottom there's C. You can program in C. On top of that, we have all kinds of default extensions which you can make use of if you want to. You've seen decision tables briefly. We looked at components, state machines, physical units, all of these things. And then kind of on the side, which spans that whole stuff there, is requirements, traceability, and product line engineering, and most recently the documentation feature, which is not yet on that slide. And on top of that, you can build your custom extensions. Well, that's not quite true, because these custom extensions obviously should be based directly on the core as well. Okay. So why would you actually wanna extend it better? Well, if we think about that picture again, we're all dealing with special domains or in a special project and stuff like that. So, for example, what we want to do is we want to forbid the usage of certain constructs because we don't feel that this makes sense in our context. Like, for example, we don't want to allow for float types, or we want to ensure MISRA compatibility, or we want to forbid pointer arithmetics. So extending a language does not mean necessarily that you add something, but you can also remove something. And the nice thing about that is that the IDE is aware of that, and if you're pressing Control Space, you won't get presented with these features, right, if you forbid that. In fact, it's impossible to write these things. Check? Okay. So another thing would be to add new types. So matrices we've seen, or vectors, but also fixed point numbers or complex numbers, special support for lookup tables, stuff like that. Adding new statements for managing memory and resources, or dealing with certain middlewares. Like I've shown you before, the component stuff. We're currently working with a customer who's writing a generator to generate AutoSAR calls for certain calls to ports, right? And by that, all of the middleware stuff gets completely removed from you as a programmer, and it's really just middleware. You don't need to deal with that stuff. The same would be true for concurrency and multi-core if you come up with the right abstractions and you actually know what these abstractions should be. Integration of verification tools. So typically a big problem in embedded software engineering is that we have a lot of these powerful tools, but they are awfully complex to use. Right? And by integrating them directly into the workflow of a developer, many things get doable, as you've seen before with the decision table verification. If you have a look at how the input to that verification tool looks like, that's probably nothing you would want to write. Or just adding new top-level constructs we've seen, the processor registers. And all of these things, there are many more things which you could do if you want to. So, status and availability. All of the stuff you've seen is open source. All of the verification tools we've used so far are also open source. You can get more information about that stuff and also download it from embedded.com. There are the next features which we're currently working on. The next one would be actually that you can switch the presentation of your program. So we've seen the table before. In some cases, or for some people, it might be easier to look at certain things in a tabular notation. For others, it might be easier to switch that over to, for example, pure text or the future graphical things. And all of that should remain editable in parallel. And that's basically finished. We're just doing the last cuts there. Next big thing which we're working on, or which we're working on together with the JetBrains guys, is graphical notations. So you can then not only visualize your state machine, for example, but also draw a state machine in a graphical representation, or draw your component diagrams, etc. Then there will be an Eclipse integration, so you can use the very same tool inside Eclipse from the guy who's actually building the language. That's currently not thought to be Eclipse, but for a user of that stuff, it can be used from within Eclipse. And with that, I'm ready through.
So you keep saying the C, although it's obviously a pretty modified version of C. Is it compatible with standard C? Can I take any library and call it?
Yeah. So actually, as I mentioned, this is not text. It looks like text. It feels more or less like text. So if you need to interface with kind of legacy code, then you need to make it available so you can call it from that IDE. And there are importers available where you can import either only the headers, or we're currently also working on an import where you can import kind of the whole legacy code, in the future also variant-aware. And once we have that, I think that's also a very, very, very powerful tool for doing refactorings. Because you have always everything available, all of the things are resolved, you can search and find all things there. So if you need to do large-scale refactorings, that would be kind of the perfect tool for that.
And the very stupid question, do you only target embedded architectures, or is it?
No, so we started actually off with targeting embedded stuff, but everything which is written in C could make use of that. And actually, there's somebody currently working on providing an implementation for C++, at least a subset of C++, because most likely we don't deal entirely with templates, it's just too complex for us to understand. And inside the same tool with a similar support, we have Java, so you can build stuff like that as well. And if you want to add your favorite language, you're very welcome. Yep.
Partially answer my question, but I didn't really understand why you reject C++ on the grounds that it's bigger and slower, because that just isn't true. It's only true when you have C++ programmers who don't understand their code they're writing.
Which is part of the problem.
And surely the technologies that you have would enable you to assist C++ programmers in realizing that they were writing bad code for an embedded context.
Well, the first part of that, of the answer is C++ is such a complex language that I don't think we are able of providing things like that. Another thing is that if you're using, for example, components, which is, so most people are using C++ because they have classes and give you an additional level to structure things. So we have components here, which actually can do more things than classes in C++. So, and as we're targeting embedded development, many of the template stuff doesn't play a role there. Many of
it's critical, because then you can get precise types with templates.
Yeah, and you get like these kinds of error messages if something goes wrong, right? And nobody can read that stuff. So there are all kinds of arguments, and regarding speed and code size, that is not an argument of mine. That's an argument actually of Texas Instruments, who's building the hardware, right? And so we asked them whether we should proceed with C++, and they explicitly discouraged us to do that. So, and that's the case for many of the other people I know of.
Good. So you performed an extension of C. What's the compiler compatibility with this?
So
with this
we're
language?
compiling everything down to C99. So, or generating, I should say, down to C99, and then from there you can go forward.
And have you, what kind of proofs do you have that actually this stuff that we generate will not introduce, for example, the same overhead that's introduced by using classes in C++?
So there's no kind of real proof. The only thing we have so far is kind of experience and an extensive set of test cases where you can always look at what we're doing. And actually for many of the things we're introducing, it's pretty obvious how you would translate them. Right? The only thing which we're adding, like for example state machines, how would you translate a state machine? It's a switch case. No. Okay. Yes. There are different ways to do that, and actually that's why all of the generators are actually pluggable, so you can exchange them if you want to. But there's a default generator which we're shipping with, and that's switch case. Okay? And if you want to replace that and optimize that, feel free to do so. But for what I wanted to say is that if you would write these things manually, most likely there's a pattern which you'd like your developers to follow. And the only thing which you add here is, first of all, they are following that pattern because it's in the generator. And second, you get this possibility to analyze the things.
Yeah, but I mean, you're still, I mean, one of the reasons you posed at the beginning is that you created this new language in order first to get rid of the preprocessor.
Yep.
But then if you're still compiling C99, then you're still using the preprocessor.
Well, in that case, you don't need, well, we need we generate defines, but we don't generate any if-thus. There's no need for generating if-thus. We're just generating that several times for different things.
Yeah, and I think you could add that the preprocessor is a sword, a two-sided sword, because a lot of projects use it to really fuck up their code. And that's an approach to get a controlled way of what many projects do with a preprocessor without doing stuff that you shouldn't really do. So it's not about replacing the preprocessor because the preprocessor we don't want a preprocessor, but it's because the preprocessor can be
it's about
used
formalizing
for things that it was never intended for.
It's about formalizing the stuff, or structuring the stuff, right? And the things which I've shown you are all more or less examples of what you can build with that stuff. And you can tweak them, you can modify them, you can completely replace them. It's all, the nice thing is it's all modular. You can pick and choose. Okay.
Okay, now I got many questions. So
Yeah, just one last thing. You're using these verification tools to check the correctness of the code.
Yep.
But do you have anything implemented to check that the compiled code will be correct? Because as we know, the compilers usually mix up, and that could result in your previous proof to be.
So all of the verifications we're doing are at best on the source code level. So many of the verifications we do are actually data flow based. So what we're doing is we generate the code out of the data. We're generating some labels in them, and using data flow we check whether we can reach those labels. That's the easiest thing to do. And then there are other things, like for example for state machines, there we're using other mechanisms to prove certain behavior of the state machine. But it's not a mathematical proof which you could use, for example, at least not currently, for certifying the software.
The easier question is, you said that it will be integrated in Eclipse.
Yep.
Does it mean that the kind of projected editor will be integrated in Eclipse?
Yep.
That's very good because it lasts for years.
Yep.
Second, about the language. It is sometimes it is somehow standardized, or is it the documentation of the extension really good? Because at first, even if it sounds very clever, the optimization and the tolerance. The tolerance notation, I was in discussions of this topic 10 years ago with a friend of mine saying, where we are doing tables with text, and we wanted to have something like this.
So it's not standardized. Of course, there's nothing where you could standardize something like that, but it's extensively documented. So we have currently roughly 300 pages of documentation for that stuff, which is first of all, how are you going to use that stuff, and also how will you build all the extensions for that stuff.
Okay. About the only point I will be not totally convinced is the way you virtualize registers. I think, in my opinion, this is mixing the problems, because the fact that to emulate the response or the hardware is always addressed by virtual platforms. Virtual platform stuff is there. You can produce some behavior on your hardware that will produce values on registers, and it seems to me that
completely agreed. The only answer I can give there is that this was a project-specific extension, so that's nothing we are shipping, but that's really an extension which we built, for example, for the smart meter project, and it was just so much easier to integrate that behavior than coming up with a whole simulated or virtualized hardware. And another interesting fact there is that when we actually started developing the smart meter software, we weren't yet sure what the processor is we were going to work with entirely, right? We just know which processor family. We don't know the hardware. We essentially did know nothing. We just started programming essentially the business logic, and at certain points we needed to somehow access that stuff. And integrating something like that is an effort of roughly half an hour, and then you're done.
Okay, so it is a first step for merely putting some behavior.
Exactly.
You can do very easily, very far without knowing your processor, without knowing even your architecture, and separating clearly the concept of the software part and the hardware part. It is the only thing that I would less enthusiastic. But that sounds very interesting.
While starting this project, did you consider the more formal languages than C?
We were thinking about that. The main reason for not considering more formal languages is that so essentially everybody in the embedded community is aware of C, right? And so we wanted not to come up with yet another language or something which people don't know about. We wanted to have an easy start and an easy transition. And this is why we started essentially with C, and C itself is already split into various languages, and you could also use a subset only of C to make it safer, whatever safer in your context means.
As that developing the UI for this, the non-textual editor, is it something that ships with JetBrains out of the box and you just customize it, or is it something that you had to develop?
So actually that's a project which is called MPS, stands for Meta Programming System. And what we build essentially is not the UI itself. We build C plus all the extensions plus the integration with the debugger. That's actually what we've done. What the underlying platform can do is that projectional nature that you in principle can mix different notations and different languages.